Hello guys, in this video lecture I will talk about the multiplexers. Like the decoders and encoders, multiplexers are the combinational circuits that selects binary information from one of many input lines and direct it to the single output line. So it means that at each multiplexer we will have 2 to the power of n inputs and n selection lines and 1 output. So suppose that we have something like that. This is a kind of the uh, multiplexer. The block diagram of the multiplexer is something like that. Here, as you can see, we have one control line and 2 input, which is called as I0 and I1, and the output, which is equal to Y. Now, how does this multiplexer works? We say that when we actually give the 0 to the S, the I0 connects to the output and transfer the information of I0 to the output. And when S is equal to 1, so it means that the input 1 connected to the Y and information in the I1 transferred to the output of the system. Now, if I want to write the table for this multiplexer, and if I suppose that this is the control line and this is the output, so I say that when S is equal to 0, output will be equal to I0, and when S is equal to 1, output will be equal to I1. According to this concept, I can say that Y is equal to S prime I0 plus S I1. So because if I get S as 0, here will be 1 I0 plus 0 I1. So it means that we will have I0, and similarly for the 1. Now, according to this concept, I can draw the actually digital circuit of the multiplexer of 2 by 1. As you can see here, according to this concept, Y will equal to S prime I0 plus S I1. Now from here I will have I0, and from here I have S prime. So here I1 and here S. So here we will have S prime I0, S I1, or we together and produce the Y. Now similarly, if we have the 4 to 1 line multiplexer, we can say that the function table for the 4 by 1 multiplexer is something like that. So as you can see, because we have 4 to 1 line multiplexer, this is the number of input. Number of input is 4. It means that we have to have 2 input, 2 control lines, and 1 output. If we have 2 control lines, it means that we will have 4 possible combination: 0, 0, 0, 1, 1, 0, and 1, 1. Now, again, we say that when we give the 0, 0 to the control line of a multiplexer, the I0 input will transfer to the output. And if we give 0, 1, means that I1 has to be transferred to the output. Similarly for all of them. So we can say that again, same as the previous one, we can write the output in as a mean term of each control line and with input. So it means that I can say that this will be equal to S1 prime, S0 prime, I0, or S1 prime, S0, I1, or S1, S0 prime, I2, and S1, S0, I3. So according to this output, I can draw its digital circuit. You can see that we have S1, S0, and you can find all of the inputs of the AND gate. Then when we OR all of them, we can find the output of the multiplexer. So the important thing in the case of the multiplexer is this: we have to know that in the multiplexer we have the control lines, and using the control lines, at each time one of the input will transfer to the out. Now if we have, for example, the 4-bit binary number and want to transfer it using the multiplexer, want to use these 4 bits in the output, how we can do it? We can use from the quadruple 2 to 1 line multiplexer. What does it mean? It means that, as you can see here, we have used the 4 2x1 multiplexer. So you can see that if you in the two slides ago, I said that this section is one 2x1 multiplexer, and also this section is another multiplexer. This OR using these two are another multiplexer, and also this one using these two AND gate are other multiplexer. Okay, so it means that all of them are 2x1 multiplexer. And also we have control line, you can see here, use all of them, and this is our enable line. Same as the decoder and encoder, we said that when we have the enable line, as you can see here, now again you can see that this is the active low. When E is equal to 0, we can use from the multiplexer. When enable is equal to 1, it doesn't matter what is the S, all of the output will be equal to 0. Now I want to analyze and show you that what's happening when enable will be active, and when S is equal to 0, how we can select the A, and when S is equal to 1, how we can select the B. Now look at here. First of all, I suppose that the enable is 1. As you can see here, we select the enable as 1. Now we can see that the not of the 1 is equal to 0. When not of the 1 is equal to 0, you can see that all of the inputs of the NAND AND gates will be equal to 0. On the other hand, we know that if one input of the AND gate is equal to 0, means that the output of the NAND AND gate will be equal to 0. For this reason, it doesn't matter what is the S. S will be don't care. So when S is don't care, it means that the output of the AND gate will be equal to 0. All of the zeros moves to the input of the OR gate, so the output of the actually this circuit will be equal to 0. For this reason, we say that, as you can see here, when enable is 1, it doesn't matter what is X, and the output will be equal to 0. Now let's look at here, and I want to show you that what's happening when enable is equal to 0. Again, here you can see that when enable is equal to 0, here when enable is equal to 0, here will be equal to 1. Now all of these inputs will be equal to 1, as you can see here. Now it means that we have to look at the value of the S. So when S is equal to 0, here will be equal to 1, and also here will be equal to 0. Again, because here is equal to 0, all of these inputs will be equal to 0. And again, because one of the inputs of the AND gate is equal to 0, means that the output will be equal to 0. And these zeros move to the one of the inputs of the OR gate. Now, we have to wait to find the another output, another input of the OR gate. Now, look at here. Here will be equal to 1. So it means that all of these inputs of AND gate here again will be equal to 1 because all of them connected to this section of the circuit. For each AND gate, we have 1, 1, 1, 1, 1, 1 up to the end. So it means that we have to wait up to the A0 comes, A1 comes, A2 and A3 comes. Now, what is the output of this gate? A0, 1, 1. A1, 1, 1 up to the end means that in the output of the AND gate, we will have A0, A1, A2, and A3. And all of this information will be transferred to the input of the OR gate. And here the output will be equal to A0, A1, A2, A3, which means that when enable is 0 and S is 0, we could select all of the A's. Now, suppose that again enable is 0, here is 1, so again all of them is equal to 1. Now we suppose that S is equal to 1. Here will be equal to 0, here will be equal to 1. Again, because here is equal to 0, all of the inputs here will be equal to 0. It means that the output of these AND gates, 4 AND gates, will be equal to 0. Similarly, the one of the inputs of the OR gates will be equal to 0. Now, let's determine the states of these 4 AND. Here again, because here is equal to 1, all of these inputs will be equal to 1. It means that we have to wait up to the B0, B1, B2, and B3 comes. Again, if you look at to this AND gate and all of these 4 AND gates, you can find that the output will be equal to B0 up to B3. These B's will move to the input of the OR gate, and at the end, in the output of this circuit, we will have B0 up to B3, which is the B. Using this circuit, which is the quadruple multiplexers, we could select one of the A or B numbers which are written in the 4 bits. Now, like decoders, that we saw that how we can design and implement the different types of the Boolean functions using decoder and OR gate. Here we want to investigate the implementation of the Boolean functions with multiplexer. How we can do it? Listen carefully. We say that if we have n variables, Boolean function of n variables, and we want to design this or implement this Boolean function using a multiplexer with the n selection line and 2 to the power of n data inputs and also 1 output. How we can do it? We say that for this implementation, if we have n variables, we choose the last one to compare with by f, and the rest one used as selection line of the multiplexer. What does it mean? Suppose that I have something like that. You can see that in this function we have 1, 2, 6, 7. All of them are the mean terms. First of all, we have to draw the truss table. Now, I will draw the truss table and will show you that how we can do it. Okay, now I draw the truss table. Now I want to fill this line. In this column, we say that everywhere we have min term, we write the 1. So 0 is 0, 1 is 1, 2 is 1, 3 is 0, 4 is 0, 5 is 0, 6 is 1, 7 is 1. According to these min terms, I produce the trust table. Now we say that the procedure is this. We select the last variable for comparing by the output and select the rest variables as the selection line. Okay, so because we have two selection lines, I look at here, I draw the multiplexer S0, S1. This is the output. Now, because we have two selection lines according to here that you can see, here is X, here is Y. So it means that we have to have 4 inputs, because we said that if we have two selection lines, means that we have 4 inputs. Because we have 4 inputs, we divide the trust table into 4 sections. Okay, now you can see that both of the xy here is 0, 0, here is 0, 1, here is 1, 0, here is 1, 1. Now we say that here is my first input, because we give the 0, 0. Here is my second input, because we have 0, 1. Here is third one, and here is the first one, I0 up to I3. Now we compare the f by z. Look at here. If we compare f by z, f is equal to z. You can see that f is equal to z. And if you look at here, f is equal to z prime, because you can see that this one is complement of this one and this one is complement of this one. In this case, f is equal to z, and f here is equal to 1. F is equal to 1. Now, according to this f, I can design the circuit. How? I say that I0 has to be connected to the 0. Z. I1 has to be connected to the IZ prime. Here is Z prime. I2 has to be connected to the 0. The meaning of 0 is the ground. Here is the 0. And I3 has to be connected to the 1. We call this one as 1. Now you saw that we could design the boolean function using 4x1 multiplexer. Similarly, for all of the boolean functions, you can design the circuits in this form. And here you can see that we can actually draw the multiplexer in this form, but it doesn't matter. You use from the trapezoid or the actually rectangular in this form. It doesn't matter. The important thing is that you select the correct inputs for the correct function in this form. Now suppose that we have something like that. F, A, B, C, D is the summation of 1, 3, 4 up to the 15. Again, because we have 4 variables, as you can see here, we have to write the 0 up to 15, 16 possible combination. And again, the last one is choose for the comparing with the f. So it means that we have A, B, C, 3 control line. If we have 3 control line, which is written as A, B, C here, we will have 8 input, 0 up to 7. Now again, because we have 8 inputs, we have to divide the trust table to the 8 sections. And again, compare this f by d0. We can see that f is equal to d. Again here, f is equal to d. Again here, f is equal to d prime. F is equal to 0. F is equal to 0. Again, f is equal to d. And for these two, f is equal to 1. So again, here is I0, I1, I2, I3, I4, I5, I6, I7. Now, everywhere is D, we connect to the D. 0, 1, and 5 are the D. And 2 is D prime, 3 and 4 are the 0, 6 and 7 are the 1. So again, using the multiplexer, we could design and implement this Boolean function. The last topic of the combinational circuit chapter is the three-state gates. In the three-state gates, we say that we have another state which is called as high impedance state. What is the meaning of the high impedance? In the high impedance, as a third state, we say that the output is neither 0, neither 1. And the symbol of the three-state gates in this form that you can see. If you remember in the chapter 1, when we talked about the different types of the gates, I said that we have one gate which is called as buffer. And the application of the buffer is transferring the input to the output. And here you can see that we have a buffer, but another line connected to this section. We called this line as a control input. And we say that when C is equal to 1, means that when comes from here, this gate acts like buffer, transfer input to the output directly. You can see that Y is equal to A when C is equal to 1. And when C is equal to 0, it means that in the output, we don't have 0 or 1. We have high impedance. And the meaning of the high impedance, as I said, is neither 0, neither 1. So it means that we break down this cable from here. Suppose something like that. So what is the application of this three gate? Using three-state gate, we can produce the multiplexer. Look at here. This is the 2x1 multiplexer. How? The select is the selection line. Suppose that here is 0. When here is 0, here will be equal to 0. And we said that when the input, control input of the three-state is 0, here is high impedance. It means that I remove this line from here. And here will be equal to 1. And when here is equal to 1, A directly transfer to the Y. So it means that Y will be equal to A. And if we select 1 here, here will be equal to 1. B will be moved directly to the output. And because here will be equal to 0, here will be removed. So you can see that using the three-state gate, we could produce the multiplexer. So if we want to design the, for example, 4-to-1 multiplexer using three states and decoders, how we can do it. Now, using just three states, we cannot design the 4x1 multiplexer. We have to use the decoder. So if we use the decoder here, as you can see in this circuit, again, we know that in the decoder, we have 2 input and 4 outputs. We use 2 inputs of the decoder as the selection line of the multiplexer, and we know that in the decoder, just one of the inputs will be equal to 1, the rest will be equal to 0, or just one of them will be activated the rest will not be activated. So here, if 0, 0 comes here, means that I0 will be 1. When I0 will be 1, and the 1, 2, 3 will be 0, it means that all of these three states will be removed. Just I0 will move to the output. When we give 0, 1 here, the line 1 will be active, will be 1, means that the rest three states will be equal to 0 and all of the outputs will be removed. Just I1 will move to the output. So you can see that using this circuit again, with selecting these selection lines, with giving input to these selection lines, we can produce the output here.